In 1637, a French mathematician named Pierre de Fermat wrote a note in the margin of a book. He claimed he had found a remarkable proof. Then he died. For 358 years, the greatest mathematicians on earth tried to find that proof. None could. This is the story of the most famous unsolved problem in mathematics and its extraordinary solution. Fermat's last theorem is deceptively simple. You know the Pythagorean theorem. A squared plus b squared equals c squared. There are infinitely many whole number solutions. 3, 4, 5, 5, 12, 13. Fermat asked, what if you replace the 2 with a 3? Or 4? Or any number greater than 2? His claim, there are no whole number solutions. Not for cubes. Not for fourth powers. Not for any power greater than 2. Ever. He wrote in that margin, I have discovered a truly remarkable proof of this theorem, which this margin is too narrow to contain. And then he was gone. That note, written in the margin of a book on Diophantus, launched one of the longest mathematical hunts in history. Was there ever actually a proof? Or was Fermat simply mistaken? In 1963, a 10-year-old boy in Cambridge, England found a library book about Fermat's last theorem. Andrew Wiles was captivated. He tried to solve it as a child. He failed, of course, but he never forgot. 30 years later, in 1993, Wiles announced he had a proof at a series of lectures at Cambridge. The mathematical world erupted. Then, within weeks, a colleague found a gap, a flaw in a technique used to control something called the Selmer group. For 14 months, Wiles worked in isolation, trying to fix it. Then, one morning in September 1994, he had an idea. He later described the moment. It was so indescribably beautiful. It was so unexpected. I stared in disbelief for 20 minutes. What was the actual proof? Wiles didn't attack Fermat directly. He went through a back door. In 1955, Japanese mathematicians Taniyama and Shimura proposed something extraordinary. A connection between two seemingly unrelated areas of mathematics. On one side, elliptic curves, equations of a specific shape, tools of number theory. On the other, modular forms, highly symmetric functions from complex analysis. The Taniyama-Shimura conjecture said, every elliptic curve is secretly a modular form in disguise. Then in 1984, a mathematician named Gerhard Frey noticed something crucial. If Fermat's theorem were false, if there were a solution to a to the n plus b to the n equals c to the n, you could construct an elliptic curve from it. And that elliptic curve would be so bizarre that it couldn't possibly be modular. So, to prove Fermat, you just needed to prove Taniyama-Shimura. Wiles proved a key case of Taniyama-Shimura. For semi-stable elliptic curves, this was enough. It meant Frey's hypothetical curve couldn't exist, which meant Fermat's hypothetical counterexample couldn't exist, which meant Fermat's last theorem was true. The proof is 129 pages long. It uses mathematical machinery that didn't exist in Fermat's lifetime. Galois representations, Heck algebras, L functions, deformation theory. This is not simple. This is not elementary. Whatever Fermat thought he had proved in that margin, it almost certainly wasn't this. What did Fermat actually have? Over the centuries, mathematicians had made partial progress. Euler proved the case for cubes in 1770. Sophie Germain proved infinite families of cases in the 1800s. By the 20th century, computers had verified the theorem for millions of values. But a proof for all n? Nothing. Most mathematicians believe Fermat had a flawed argument. Perhaps an error he never noticed. In a proof he never wrote down. The margin was too small. Not because of arrogance, but because the real proof required centuries of mathematics that hadn't been invented yet. Fermat's last theorem isn't just a curiosity. The mathematics developed to solve it became one of the most fertile areas of modern mathematics. The connection between elliptic curves and modular forms now underpins something called the Langlands program, a vast network of conjectures linking number theory, geometry, and analysis. Sometimes the greatest advances in mathematics come not from solving the problem directly, but from the journey to get there. And there's the human dimension. A boy in a library. A problem that captivates him for life. 30 years of secret work. 14 months of desperate repair. And then one morning, the breakthrough. Fermat's last theorem stands as a monument to what mathematical obsession can achieve. To the idea that some problems wait for their moment. That the tools needed to solve a question from 1637 might not exist until 1995. That the person destined to solve it might have first encountered it at age 10. Fermat's last theorem. Part 6 of the Big Questions. A series on the deepest problems in philosophy and science. Previous episodes covered why there is something rather than nothing. The mystery of free will. The hard problem of consciousness. The P versus NP problem. And the paradox of infinity. Whatever questions remain, this theorem teaches one thing. The most stubborn problems sometimes yield the most beautiful mathematics.